Okay, so I'm kind of starting in the exact same spot that we started yesterday when we started to investigate zero exponents and negative exponents, right? And you also note that today we're going to all be together. I think tomorrow I'm going to split you up into your groups and it'll kind of be a 2-day assignment thing. So today we'll do the all together portion, all right? So yesterday we started looking at like powers of 5. Today I want to look at powers of 10 because powers of 10 provide us this wonderful shortcut for looking at really large or really small numbers, and that shortcut is called scientific notation. You guys might have heard of it, yes? Have you heard of scientific notation? I assume most of us probably have. But I just want to make sure that we're solid on that before we move on. So scientific notation is the main theme of this little assignment we're going to do for a couple days. Scientific notation is all about powers of 10, so I thought we could just investigate the basic powers of 10 first, just like yesterday we investigated the basic powers of 5. Okay? So can you guys help me out? Let's fill in this chart. Where should I start? Where's an easy spot? So the 0 power is a good spot to start now, right? What's anything to 0? 1. Anything to the first power is itself. And then you got to start thinking. So 10 squared is 100. 1,000. Let's go back this way. 1 over 10, right? And this one then is 1 over 100. See, I don't even have to think very hard. I just look over there. So this is 1 over 1,000 and 1 over 10,000 to get a comma in there. Okay, so there's some of the powers of 10. Those actually aren't even that big of powers of 10. What we're really interested in usually in scientific notation, their true value, which you'll see in a couple application problems I gave you, which aren't bad, is that they're used for really big or really small things. For instance, in chemistry, I think I gave you a problem on this, even in chemistry 1, like the most simple chemistry you can possibly do, you start to look at the sizes of things like what? Really, some really small things that we deal with in chemistry. Atoms. And atoms have component pieces like electrons, neutrons, protons. Well, you're going to look at the size of an electron, proton, and neutron in one of the problems I gave you, and it's like times 10 to the negative 27th or 31st power. Just way down the chart that way. Does that make sense? So that's why you need these powers of 10, this scientific notation that we're going to start working with. So I want to write these not as fractions, since they're powers of 10 based on humanities achievements are the easiest way to write something as a decimal. They're not the only way. There's all kinds of other more complex ways that the Egyptians did and stuff. They didn't use powers of 10. They used powers of 60. Made things a lot harder. Powers of 10 lets you write 1/10 as what? 0.1? And 100th as 0.01? And 1/1000th as 2 zeros and a 1, and 10,000th as 3 zeros and a 1. So I think looking at these simple examples should give us some insight into how to use scientific notation. Okay? So you're going to have a variety of problems in the book, but they're going to start out with baby steps. So let me show you a couple of the problems they're going to start giving you. They might ask you for 10 to the negative 6th power just to compute these, or 10 to the 9th power. They might ask you to write things as a power of 10, like 0.0, I don't know. I'm just going to put some zeros out there I didn't even count, right? Or they might ask you to go more zeros. For really small things, okay? So you should be able to convert those into powers of 10. That's going to be essential for scientific notation. So there's a variety of ways you can do this, okay? It's not just one way. So my favorite way to do 10 to the negative 6th power is to do what we just did. To say it's 1 over what? Would be 2 more slots over here. So it'd be 1 over...
wouldn't the 10 to the 9th be 10 to the negative 9? Right there.
I just picked a couple different examples.
No, I know, but you just, isn't that 10 to the negative 9?
Yeah. No, I meant to write this as 10 to the 9th. These are totally separate problems.
Oh.
They do not relate to each other.
Okay.
They look really close, don't they?
Okay.
Sorry. Good point, Sheridan. Ha.
Wait, how many?
Separate examples, okay? These ones we're going to turn into decimals. Those ones we're going to turn into powers of 10. Does that make sense? Problem 1, problem 2, problem 3, problem 4. Good question. That was confusing the way I did that. My mistake. Yeah, Richard. So 10 to the negative 6. We're going to start out with that. 1 over 1 million. See, and there's some kind of factual knowledge that really helps with powers of 10 as well. And you need that for chemistry, you need that for biology, so we're going to learn it in here so that you already have it as well. So let's learn our powers of 10 before we even work into this as words. And I think this is useful for all kinds of reasons. So I want you to know up to 10 to the 12th for now. My physics kids have to memorize the metric prefixes for up to 10 to the 30th and down to 10 to the negative 30th. So you're starting with just a little piece of that. Okay, so 1 second, Lindsay. So we're going to just know the powers of 3. That's sufficient. We could go more, but those are the most common ones that come up a lot of the time, different places. So, Lindsay, do you have a question now?
I just noticed that, well, at least with the positives, the number that the 10 is raised is the number of zeros that are after.
Yeah, great. So that's one of the rules we're going to try to write down in a second. So you just already noticed it. Yeah. Very nice, very nice. That's what we're going to write down so that we all have a guideline. But knowing just powers of 3 as words is also useful for all kinds of different things, okay? I think you probably have heard of these before too. Let's start with the positive ones. What's 10 to the 3rd? Does anybody know the metric name for that?
10 cubed.
Starts with a K. As in like kilobyte.
I was gonna say
1,000 bytes of information. So the metric prefix for this is kilo. So computers use this, for instance, right? Whenever you look at file extensions and it says how big they are. If you see KB, that means 1,000 bytes of information. Kilobyte. Okay.
Is that only for 10? Like 10?
They're all based on powers of 10. Yeah.
Is
So if there's 16 kilobytes of information, then that's 16 times 1,000, which is what we're going to do in a second.
oh,
Okay.
so like if you had like 11 to the 3rd power, it wouldn't be per kilo.
Then you're not in a base 10 system
okay.
anymore.
Okay.
So exactly, good question. Sure. So anybody know 10 to the 6th? Now that I gave you the computer analogy, I bet somebody might know. What's the metric name for 10 to the 6th? What's the next biggest size in computers, for instance? Kayla? Mega is correct. So this is mega, as in megabytes. That's 1,000,000 bytes of information. So if you have 12 megabytes, then you have 12 million bytes of information. Okay? That's scientific notation, whether you see it or not. That's what that is. Okay? So 10 to the 9th. Anybody know the next biggest size? Think about files that you've seen. It's gigabytes of information. But it doesn't just apply to computers, right? That's just one thing. That's bytes of information. It could be gigatons or gigameters. That'd be really long, right? Billion meters long. 10 to the 12th, anybody know that? This is what size a lot of hard drives are right now. It's tera. Yep, okay. So let's go with the smaller ones. So these, I want you to know them all. I might not make them required, but they'll come up as like extra credit on quizzes, which our first quiz is going to be tomorrow or Thursday. See? So 10 to the 3rd, negative 3rd, so small, 0.001. What is that? What? I think I heard it. Close, yes. Milli. Got that one, good. And then 10 to the negative 6th. Deci is like 10 to the negative 2nd, and that's not as common, so I'm not going to have you know that one. 10 to the negative. Okay, so I think we still need to finish our metric prefixes. Colton told me next that 10 to the negative 6th was micro, the prefix for it, and 10 to the negative 9th, I think you guys have definitely heard of this one, nano. So whenever someone tells you about nanometers or something that's nano size in terms of how small it is, you know they really mean 1 divided by 1 billion. So besides knowing the metric prefixes for these so that you know things like how much that actually means when it says megabytes in your computer or in terms of how many pictures you have or something like that, these are useful all over the place. It's also useful just to know like the major sizes, how much they are in terms of what the size is. So let me put that up here as well. So 10 to the third, that's 3 zeros. So I think that is 1,000. So that's 1,000. 10 to the 6th is 1 million. 10 to the 9th is 1 billion. And the next would be trillion. And you can keep knowing that's kind of about as high as numbers go for us in everyday life, at least. Definitely not in science, though. Numbers go a lot smaller than this in science as well. I think you'll actually see a problem involving electrons and protons and the sizes of how much mass they have and such. And they're really, really small inside those atoms. So you're going to get way down below here. But for right now, let's just leave this as the thousandths. So this is 1,000 if it's 10 to the negative third. If it's 10 to the negative sixth, it's 1 millionth and 1 billionth. And of course, you could keep going down into stranger numbers that you might not have heard of, but which will come up in chemistry classes and such. So that's why I'm having you know these. They'll definitely be on your quiz. They might be bonus, but you want to know. Okay? All right, so let's start to look at the kinds of problems the book is going to give you. So we had that table of powers of 10 up there a second ago. I think if you go back and look at that table, my class, pretty much almost everybody in the class seemed to guess the rule from the table. So go back and look at your table and see how many zeros are in each one of the powers of 10 and how you might look at that. So you might want to pause the video right now and go back and look at how many zeros there are versus the exponent for each one. Okay? So if you investigated that, you should find out that if there's a positive exponent, you have the same number of zeros. A better way to think about it, as we'll see in a second, is the same number of places as the exponent. So if I've just got 10 to the negative, let's do positive, 10 to the positive 8, that means I have 8 zeros. So I go 1, 1, 2, 3, 4, 5, 6, 7, 8, and I can put it in there. Now if you want to check this the more traditional way, you can start with, here's the decimal place, and you go 1, 2, 3, 4, 5, 6, 7, 8, and there you have it. It definitely works. So I highly recommend being flexible with this and checking it multiple ways. If you look at the negative exponent examples, I think you'll find that the powers of 10 at least have one less zero or one less place than the exponent. So if it's 10 to the negative sixth, we're going to start with a point and we're going to put 5 zeros in before the 1. So if you check that the more traditional way, you're going to see that it moves from right here and goes 1, 2, 3, 4, 5, 6. There you go. Same thing, works out both ways. So I really like to think about it that way though. All right, so we did put those powers of 10 into standard or regular number notation. We could also, of course, take a number that's in standard decimal notation and put it in a power of 10 notation. So we could say this is 10 to what power? Well, since it's less than 1, since it's going to the right-hand side, you should guess that it's going to be a negative exponent. So negative what? How many zeros? 1, 2, 3, 4. So go back to the rule we just discussed, and 4 zeros means this is going to be 10 to the negative fifth power. You can check yourself. 1, 2, 3, 4, 5. There it is. Okay, so how about 0.01? That's also going to be a negative power, I think. So what negative power is that? We could do it the old way. 1, 2, or we could say there's 1 0, so this has to be 1 bigger. Okay? Same thing here. When you have a large number of zeros, be it a negative exponent, like this one's going to be negative. I'll trust it that you can do the positive ones yourself. If you've got a lot of zeros, my advice is this: group them in threes. Here's what I mean. It's really hard to count those zeros and not skip one or something like that. So group them in threes, and it makes it so much easier. So 3, 6, 9, 12, 15. So I've got 15 zeros, so that means this should be negative 16th power of 10. Okay? Let's look at the full-blown version of scientific notation now. Okay, so we looked at powers of 10, so now I'm going to move up into all numbers that can be expressed in scientific notation. So powers of 10 are like an integral part of that. They're probably the most important part, but they're not all there is to scientific notation. So I wrote my definition. It's not formal, but this is my definition of what scientific notation is. What does it mean to be in scientific notation? So numbers that are in scientific notation are those that are written where the decimal point is between the first and the second number. It doesn't matter how many more numbers are after that, but it's got to be after the very first number. That's where that decimal place has to be, okay? Another thing about scientific notation is you've got to have a power of 10 in there. Remember, scientific notation is used for representing those really big or really small numbers. It can be used on any number though, so I just kind of picked 3 fairly random numbers here, and I wanted you to think about which one of them is in scientific notation. So if you want to pause the video and try to pick, there's only one of them that's in scientific notation, you might want to do that now. So after you've thought about it for a second, I think you'll find that only this guy is in scientific notation. It's got a power of 10 that it's being multiplied by, and the decimal place is right after the 5. So we could, of course, convert it to normal notation. Now let's think about how to do that. How would we convert this to normal notation? Well, power of 10, it's bigger than 10 to the third, so thinking about our prefixes, we might say, well, this is like bigger than 1,000, maybe it's 10,000. So I think that's the way to do it. So really, this is like 52,300. So I can do that in my head already. If you're not that comfortable with it, though, with using those reference points, the 3, 6, 9, 12, of course, you can just change it into a number first. So there's different ways to do that. The way you probably learned is to to move the decimal place 4 spots, right? So which way should we move the decimal place? If we're multiplying 5.23 times 10 to the 4th, is it going to get bigger or smaller? That's what you want to ask yourself first. Well, obviously it's going to get bigger. So to get bigger, I think the decimal doesn't go this way, it goes this way. So I'm going to move it 1, 2, and then I have to add some zeros to get those last spots. So 3, 4, so 2, 3, and I think there's 2 zeros in there. That's where the new decimal place is. 52,300. That's what I was thinking, just thinking about where it was at between powers of 3. So that's one way to do it. Let's go back and think about our other way to do it. So the other way to do it, besides moving the decimal place like that, would be to think about how many zeros we have. So our rule was if it's a positive exponent, you need 4 zeros. But it's not really 4 zeros. Do you see 4 zeros here? It's 4 places, so you've got 1, 2 already taken up by the 2 and the 3, so then you add 2 zeros to get those 4 places, and that's consistent. Okay? Okay, let's look at these last 2 problems here. So we wanted to convert them into scientific notation since we agreed that though they both had powers of 10, the decimal was kind of in the wrong spot on each one. So what I thought we'd do to do that, and something I really encourage you to do as well, is to convert it into just normal notation first, standard notation, and then go back to scientific notation from there. So I think that makes it simpler, and also it's just a good way to start working with all the different notations. Up to you though. So times 10 to the negative 4th, which way would that make us? If we're multiplying by times 10 to the negative 4th power, are we going to make ourselves smaller or bigger? And I think you should quickly come to the conclusion that negative 4th power is going to make us smaller. So think about it. If you move this decimal place this way, are you getting smaller? I don't think so. I think that's making that number bigger. So I need to move it to the left in order to make myself smaller. And I need to move it 4 times. So 1, 2, 3, 4. So there it is. Looks like I'm going to put 1 0 in there. And so what do we have? We have 0.060854. Okay, so now I'd take that standard notation number and write it in scientific notation. That's one way to do this. So now to be in scientific notation, that decimal point actually needs to be here, right after the first real digit that's not a 0, the 6. So I need to move it twice. So that's 6.0854 times 10 to the negative 2nd power. Okay, and you can see negative 2nd power has 1 0 in front. That matches our rule from earlier. So let's think about it. If we hadn't done it that way, let's go back to the original problem and think about how we would have solved this problem. So which way would we have needed to what will we do with this exponent to change it? So we'd say, well, we know 6.0854, since that's where the decimal place needs to be. We know I'm times 10 to a certain power. So what is the power that I need? So we got a -2. So moving to the left means I think we need to like move that to the left by 2. So see, that's kind of hazy and a little bit mysterious, at least to me. So I really like changing it into a normal number first and then being really confident about my new scientific notation. Let's try that same method over here. So this guy I'm going to change into regular notation. So I need to move the decimal place 7 times. So I'm going to move it 7 times. So there's 1 time. Looks like I'm going to need 6 zeros. So 1, 4, 3, 1, 2, 3, 4, 5, 6. And there will be my decimal place. I'm just going to check. So let's see. 1, 2, 3, 4, 5, 6, 7. Sweet, I'm set. I'll put my commas in. So there's a comma there and a comma there. Looks like that number is 143 million. That would have been a good way to think about this as well. Is 10 to the 6th, we learned was millions, but it's 14.3, not millions, but 10 millions. And 14.3 10 millions is 143 million. So there's another way to think about it. So it's good to be flexible with this stuff. So if we write it in scientific notation, now we can say, well, how many places after that are there? There's 1, 2, 3, 4, 5, 6. I've got to count these 2, 7, 8. So it's 14.3 times 10 to the 8th power. So if you wanted to think about it just going from here straight up to here, 1.43, you'd think about, well, I need to move this decimal place 1 that way, and that gives you the 8th power. I again think that's kind of vague, so going to the standard notation and then building back up is probably a safer way to go, and also just gets you working with all those different forms. So here's a little application. We're going to look at Saturn in terms of both its diameter, how far it is across through the center of the planet, and we'll also look at how far it is away from the sun. Those numbers are obviously both pretty big, especially the one that's measured from the sun in terms of its distance. So they both require scientific notation to work with. So first, let's just convert them into the other form. So let's take that diameter and change it, which it's scientific notation now. Do we really need scientific notation on that? Since it's only 5th power, I'm not so sure. So let's convert that to standard form. So what is that number in standard form? I guess I'll write it down one more time. So again, we could do different things. So one of the things we learned is we could move the decimal place. Since we're going to make it bigger, we need to move it to the right. And we could move it 5 times to the right. So I'm going to do that. Let's see. 1, 2, 3, 4, 5. There's my decimal place. You could just start right here and go over if you scoot that out of the way on your paper. And then I'll put in my comma. So apparently this is 120,000 kilometers. Let's make sure that this makes sense the other way we talked about things. So if it's a positive exponent, that means we need that many places, that many zeros, if you will, but they're not all zeros in this problem. So we need 5 spaces after the 1. So if we go 1, 2, 3, 4, 5, check mark. That's the way to do it. So there it is, 2 different ways. So Saturn has a 120,000 kilometer diameter if we're thinking around the planet. So like its diameter this way. That's how far it is across. So fairly large. It'd be interesting to compare to the Earth. I think that's quite a bit bigger. Anyway, if we talk about its distance from the sun, though, that's such a huge number. In fact, I think thousands, millions, billions. It's in the billions. I guess it's not that big of a number, but it'd be more convenient in calculations to treat that in scientific notation. You'll see that either this year or another year. So let's convert that number into scientific notation. So again, you can do it both ways. You can take your decimal point, which is right here, and move it to the right spot. So I need to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 1.427. Everything else is zeros times 10 to the 9th power. let's make sure that makes sense. So we're supposed to have 9 places after the 1, and I think there's clearly 9. You could also have done this just by thinking about the metrics. 10 to the 9th is billions, that's in the billions spot. So you could just say, hey, this is billions. I know 10 to the 9th is billions. So you can just be like, bam, 10 to the 9th right there. So there's another option that you have in a problem like this. So that's all you're going to do on your problems. I wanted to take this a little bit further, because if in physics or any other actually applied class that you might take and actually use this stuff in, if you were to use either one of these numbers, you'd be wrong. That's because when you do computations involving planets or anything in the metric system, you can't use kilometers. Everything in the metric system has to be reduced so that the metric prefix is gone. So even though this would be fine for now, this is kilometers or kilometers. We learned what kilo meant. It means times 10 to the 3rd, right? So how many meters is this? If you were going to use these numbers and actually do something with them in physics, for instance, you'd have to change them into meters. So really, there's another piece of scientific notation hiding out here. That kilo means times 10 to the 3rd for both of these. So really, this guy is 1.2 times 10, and I think we're going to have to move it 3 more spots over to the 8th. That's how many meters, a meter being like 3 feet, that's how many meters Saturn is across. And 1.427 times 10 to the, we had 9th and 3rd, I think that's going to be 12th, is the number of meters that it is from the sun. So that's something nice to know, because later in classes, if you're doing computations with these, they have to be in meters, or you're not going to end up with the correct stuff. So there's a good reason to know your metrics. Okay, see you next time.